Now let's resume problem 4. Yes. How about I post the answer to the PDF and as a PDF file sometime. I'll give you 2 more days to work on it. I'll post on the weekend, like Saturday. Awesome. Okay, so what is the TLB? Free question. You'll see this question here again. What is the TLB? What's the benefit? Why do we need one? You can say it's cache translation process. You can say it's avoid page walk. As long as you explain it in a way that you understand that TLB is the caching structure that allow you to quickly look up what's your physical address. You can also say cache EPN to PPN. That's also a perfect answer. Reduce the overhead of lookup since it's in SRAM. It's fast, right? Assuming that your memory access take 100 cycle, you have to go to DRAM and take 100 cycle. The system has 2-level page table. TLB access take 1 cycle. L1 cache access take 1 cycle. If I have a TLB miss, L1 cache hits. How long does it take for me in total? 2-level page table. So if I have 2-level page table to get the physical address, how many cycles do I need? So let's it's 202. Yes, you got it correctly. So the chain of what need to happen is first you check TLB, right? Then it's a miss. So you go to do page walk. And once you have the page walk, that's when you have the physical address and the cache access take 1 cycle. So this is a cache access. Right? Check TLB take 1 cycle. Because we said accessing the TLB would take 1 cycle. Page walk, you have to go to the memory twice because it's 2-level, right? 2-level, basically you have to go to DRAM twice. Each time it's 100 cycles, so the page walk will take 200 cycles. Then you do the cache access 1 more cycle. In total, it's 202. In this question, if you, let's say you assume things like VIPT and you assume that once you have the physical address back, it's instant. You said 201. If you make the assumption clear on your answer, I accept that as well. Yeah, so as long as you have state your assumption, that helps as well for me to figure out what is your thought process on that number. But the answer that I aim for is 202. All right. Oh, the answer is great question. So the question is why do we have to access DRAM twice? So when I said TLB miss, what does that mean? It means that I don't have my physical address, right? I don't have my physical address. And in order for me to access the cache, I need physical address for the tag bits. Basically, I need PA for tag bits, right? Which means that I need to get my physical address, and the physical address is not in the TLB, so I have to do the page walk. When I do page walk, it is the same process as this earlier question, right? Go through this table. This table is in DRAM, which means that when I need to read to DRAM, I have to access DRAM. Unlike this question where I said it's only 1 level, the question in here, right, in here said we have 2-level. We have 2-level page table. It means that we have to go through that table twice. You have to go through that table twice. The first time you go through the table, it gives you the pointer to the next location of the next table, right? So what you ended up with is you go to DRAM twice because you have to consult 2 different tables, both of which are in DRAM. So that's why it takes 200 cycle. Then once you have the physical address, you go check the cache. Is my data there? So that's one more cycle, right? So is it more clear? It's just because we have this. So we have the TLB miss. Basically, because we have the TLB miss, we don't have my physical address. So to get that, you have to do a page walk. And that's why I said virtual memory is also important to performance, because we need to figure out how to quickly get the physical address, right? So same assumption, two-level page table, TLB access take one cycle, cache access take one cycle. I have TLB hits. I have TLB hits. L1 cache hits with PIPT cache. Feel free to explain your answer. That's when your assumption comes into play here. I have the TLB hit, PIPT, right? So the first thing I do, I have TLB lookup. Once that's done, that's one cycle, right? You get your, now once it's done, you have your physical address, then you do cache lookup. This is one more cycle, right? So in total, 2 cycles. So there's absolutely no way your cache lookup can happen in parallel with the TLB access, because it's PIPT cache, right? Now, the next question say, hey, what if I use VIPT? I have virtual address coming in here. I start the TLB lookup. Just take one cycle. This is ambiguous because the question, actually, I have to be honest here, my question is bad because I said cache access take one cycle, but I didn't say how much does it take to get the set and how much does it actually take to compare the tag, right? So if I say getting the set and compare the tag, like compare the tag is free, so basically get the cache set, one cycle, and say compare the tag, let's say it's free. The answer is one cycle. But if I use VIPT, but somehow getting the cache set is one cycle, and then to compare the tag, you need another cycle, then this answer in 2 cycles, right? So that's why I said this question is bad, and sorry again if this confuses you, because I need to tell how much time does it take to get the cache set and how much time does it take to get the tag. All right. Now, the last question. Considering that the page offset is a piece of information shared by both VA and PA, how much data? Why do you have to go to TLB if it's virtually indexed? Oh, because it's virtually indexed. So VIPT, virtual address for the index. But we need both the index and the tag to figure out where is my data. Is it in the cache or not? And you need the physical address for the tag because it's VIPT, virtually indexed, physically tagged. Yeah, so you need to go to the TLB to get your physical address to compare the tag. Why do we need physical address for the tag? Because you can run into the case where 2 programs has the same virtual address, happen to be 2 different programs, so they go to different location, to different physical address. That's bad, right? So you need physical address for the tag to be able to tell who are you. All right. So let's consider the last thing. Now, this last question. Page offset is a piece of information shared by both VA and PA. How much data can a 6 to 56 entry TLB structure cover? Like, what's the range of address can I hold? If I have 256 entry TLB, 4 kilobyte page size. Now, each entry of the TLB, right? Each entry store VPN to PPN, right? So you have one physical page number per entry, 1 PPN per entry. So in one entry, how many kilobytes of data am I covering for the TLB entry? How many kilobytes of data? I can cover one page, right? So that's 4 kilobytes. And I have 256 entry. There's going to be 4 kilobytes multiplied by what? 256? How much is that? 1 megabyte of data. This is small. It's quite small. You buy a CPU and your TLB holds the range of 1 megabyte. Whatever page you store, if you have to go over multiple pieces of data that span more than 1 megabyte, you might have some TLB misses, right? So this is an open-end question. This question is not open-end, it's 1 megabyte. But once you see this number, I like my hidden agenda from this question is I would like you to think, right? That hey, if my CPU only have say 1,000 entry or maybe even 2,000 entry, but my page size is 4 kilobytes, right? Let's say I have 2,000 entries, I can only cover 10 megabyte range. That's not a lot, right? That's not a lot. So I might have a bunch of page walk. I might have a bunch of page walk. My program can run slower, right? So these are things that can affect your performance, the performance of your application. How many people use virtual machine before? How many people use virtual machine before? I'm gonna motivate it with something. Do you realize that it actually get even slower? Virtual machine is slow. It can be really slow. Yeah, with the Windows subsystem for Linux, right? It's also a virtual machine, right? Uh, WSL, I think it's more like a Docker, so it's a little bit different. It shares structure with the OS. But in a virtual, like full-blown virtual machine, you first install something on it, right? Like Linux or Windows. You basically have an OS within another OS, right? Are you guys with me so far? By the way, this doesn't go into your exam. This is beyond the scope of your exam. I just want you to think with me. So it's an OS within an OS, right? So now let me draw this out. VM, right? This is VM side. And then this is host OS. Host OS is basically the OS of your machine. So let's say you have a virtual machine running on your Windows PC. The host OS is Windows, right? So when I have an address, in the host OS, how many times do I have to check to go to DRAM in order to do translation? How many times? If I have to do page walk, right? If I have to do the page walk, you have to go to DRAM once, twice, 3 times, 4 times before you can get to your data, right? So that's in your host. The VM has its own virtual address, right? So if I have an address in here, what does it mean? I have an address in a VM. I want to access some address inside the VM. All right, think with me. So inside the VM, how many times that I have to do to get my physical address? Yeah, it's page walk within the VM that trigger the page walk externally. So let me go through this example. This is one of the big reasons why VM can be slow. When you have an address in a VM, right? This is a virtual address in your program, right? And what you have to do is you need to get a physical address, right? You need to get a physical address. So I have VA, right? You go to the first step, second step, third step, fourth step, and that's when you have the physical address, right? Physical address. The problem is inside here, VM is a program. So when I do translation, I go to the page table. That page table is a virtual address on your host. This is guest virtual machine. Guest virtual address. Guest physical address, my bad. Guest physical address. Guest page table level 1. Guest page table level 2. Guest page table level 3. Guest page table level 4. Right? Each one of this is a VA in the host. Because it's a virtual machine is a program, right? Are you guys with me? Every time I walk the page table inside the virtual machine, I say, hey, go to that location in the page table, and I think that's a physical address. But it turns out because you have a virtual world inside another machine, that is actually the virtual address of your host OS. So from host VA to get to your data, how many DRAM access is this? Now you're on the host, but you just get one virtual address. To get to your data, how many DRAM access is this? Four to get the physical address, plus one, this is to get the PA, this is to get the data, right? Again, over here is 4 to get the physical address, plus 1 to get the data. 4 to get the physical address, plus 1 to get the data. 4 to get the physical address, plus 1 to get the data. Right? And now you have the guest physical address. This is guest physical address. This is again host virtual address, right? So to get to the physical address, 4 more to get to the actual physical address. So you add everything up. This is 24 DRAM access. So now you see why things get a lot slower if you don't do something with this, right? Okay, I'm not going to ask a complex question, but do you see the problem here on why? One of the reasons why VM can be slow. Yeah, I'm recording, I think, but it's not going to be on your exam. Great question. That's like virtual machine kind of have two types, right? How about Docker? How about Docker? So let me put it this way, right? Things depends on how you implement it. But let's say you download a virtual machine, right? Let's say you download a virtual machine, you install an OS on it again, right? What you're gonna see, this technique is called nested paging. Oops, sorry, wrong spelling. This is called nested paging. It's a technique to get to the physical address from the virtual machine. This is 24 DRAM access, which is actually a little bit absurd if you think about it, but that's the cost you have to pay, right? So now let me expand onto your question. When you said isn't VM has two types, can you expand on that comment a little bit so I know exactly what you're thinking about? There's no wrong answer. I just want to be able to like start from that point. Oh yeah, so you can. That's a great comment. Awesome. Actually, I love what you're getting at because these are some of the things that hardware can help, right? So there's quite a lot of techniques nowadays that has been proposed, some of which involve like having a hardware MMU tackling and solving some of these nested paging. And it's a great comment because you're getting at something that actually happened, right? So one thing you can do is to have the hardware help managing this translation or at least work with the OS to reduce the overhead of nested paging so that you don't have to do 24 DRAM accesses. There are techniques that can flatten this, go and route it out to like 5 axes, for example, right? And there's also more techniques that can further reduce the access. That's why it's not always bad when you when you use virtual machine. But the default as you understand it, right? As you understand virtual memory, as you see it from the lecture, you think about VM and including, to be honest, even like a software VM that you use right now, you're likely to do 24 DRAM access for page walk. And that's why I think like a TLB is really important because you want to be able to cache them. There's so more caching structure that's built to support it. And there's also like another body of research that look into does this four-level page table make sense? Can we do something shorter? For example, the idea that was suggested by the student in this class, right, on Tuesday is a legit idea. Why don't we have one table? Why don't we just make it such that a flat table can work if you can go with flat table, right? These are legit idea. It just basically have to have some additional fine tuning and see make sure that it works with uh the scenario you're trying to run, right?